Okay, welcome back, guys. I need you to be on pages 125 and 126 in your workbook. It's exponential equations using logarithms. So if you were to think back to when we did page 112, we actually solved exponential equations without logarithms. And if you remember, they were in this form, but the difference was we would have things like 2 to the x plus 3 equals 8 to the 2x minus 9 or something like that. And the thing that we found with all of those problems on page 112 was that these bases could somehow be converted into the same base. And so we didn't need to use calculators. We would say that this was 2 to the x plus 3 equals 2 to the third to the 2x minus 9. All right, hopefully you're remembering these. Then this would be 2 to the x plus 3 equals 2 to the 6x minus 18. And then we said, well, since the bases are the same and the expressions are equal, the exponents must be equal. Again, this is the whole one-to-one property about exponents. We didn't talk about it back when we were solving these equations, but we have since talked about it regarding logarithms and exponents. It's one-to-one, meaning that anytime we pick a y value, we can say, oh, there is only one x value down here on the x-axis that gave us, sorry, that was totally drawn incorrectly. We can say for any y value we pick, so let me say that it looks like this. So for any y value we pick, I went backwards. For any y value we pick, we can say that there was exactly one x value down here that made that happen. So if I've got 2 to some power equals 2 to some other power, those must have been the same values right there. And then we just set them equal to each other. So x plus 3 equals 6x minus 18. We would solve, so we would get 5x equals 18. 9 equals 21. So we got some x value here, 21/5, let's say. But as you look at the problems on this page, you'll notice very quickly that there is no way that we can get this base and this base down to the same value. All right, there is no power of 17 that equals 62. And so we're going to have to use our calculators for these, and we're going to have to use logs. All right, and the reason we're going to use logs is because we just discovered a change of base formula, or we just practiced with a change of base formula that's going to help us solve it using logs. So the first thing we're going to do is we're going to rewrite this in logarithmic form. All right, so again, this is the base of the exponent. It becomes the base of the log. So this is log base 17. And then these two flip-flop positions. So it becomes log base 17 of 62 equals x. And again, just like we did on the previous problems, we could say 17 to what power equals 162, and we could guess that it's between 1 and 2, much closer to 1, because 17 squared is 289. That's pretty far away from 62. So we're going to guess that this is somewhere between 1 and 2, but let's use the change of base formula to figure it out. So this is log base 10, or base e, whichever you prefer, of 62 over log base 10 of 17. And again, you don't even need to write that 10 in there. We haven't done that in the past problems, but without writing the log, it's still assumed to be base 10. So you could actually be writing it like this. All right, I'm going to do that in my calculator. And so I'm going to get log of 62 divided by log of 17. And again, I think it's somewhere between 1 and 2, much closer to 1 than 2. Yeah, and it's 1.4566. This says round to the nearest 10,000th. So we're actually going to go to the fourth place and round one more. So this is going to be 1.4567 is our answer. Right, that's best case scenario, where it's just a plain old base here with some exponent and a base here, or just a constant right here. All right, so how about you stop and try number 3 right now, and then we'll move on. Okay, so hopefully you did all right with that one. So again, we're going to rewrite this in logarithmic form. So the base of the exponent becomes the base of the log. And then we're going to flip-flop these two. So this is log base 9 of 29 equals n. And again, if I were just to estimate, I would say 9 to the first is 9, and 9 to the second is 81. So 1 is too small and 2 is too big, so it's going to be somewhere between 1 and 2, probably closer to 1, because 29 is much closer to 9, which is 9 to the first, than it is to 81, which is 9 to the second. And again, we're going to use the change of base formula, so I'm just going to do natural log this time just to mix things up. So this is natural log of 29 over natural log of 9. All right, I do that with a calculator. Natural log of 29 divided by natural log of 9, and I get 1.53. Actually, I was wrong there. 1.5325. It's actually slightly closer to 2 than it is to 1. Okay, let's scooch down to number 9. All right, so problem number 9, you see, starts to get a little bit jazzed up here. Instead of just having a base with a plain old x as the exponent equals some constant, we now have a coefficient here. Our exponent is not quite as plain as it was before. There is one additional step that we need to take in these problems where there's a coefficient right here or later, maybe a constant that we're doing, and that is to isolate this term, or this factor right here. We want to get the 13 to the 7x by itself. Right, so what we're going to do is, in this case, we need to remove that 8 through division. It's multiplied by the 13 to the 7x, so we're going to divide it. So this would become 13 to the 7x equals 73 over 8. I'm going to suggest to you that you leave it as 73 over 8. And let your calculator do the work. First of all, if you round this, actually this one's not too bad because an 8 denominator should end in 3 places, but a lot of them won't be quite that nice, and you'll end up with a very long decimal that you need to cut short. So I would just recommend putting that into your calculator as is after we write it in logarithmic form. All right, so we're going to rewrite it as a log. This is the base of the exponential, so it becomes the base of the log, and then these two flip-flop. So it's going to be 73/8 equals 13 to the 7x. Oh, sorry, no, 7x. We already used up the 13. Okay. I need to use the change of base formula on this side. So I'm going to write it as log 73/8 over log 13. And I'm going to get a value that I'm then going to set equal to 7x. So let me do this in the calculator first, and then I'll set it equal to 7x. All right, so if I do log 73 divided by 8, and the parentheses, divided by log of 13, I get 0.8620. Now it's telling me that this and this have to be equal. All right, so I start a new equation that says 7x equals 0.8620. Divide both sides by 7. So 0.8620 divided by 7. And I get 0.1231 as my answer. Right, it's a little bit harder at this point when there are exponents on here that aren't just plain old x to get a good estimate, which is why I didn't try and estimate it this time. This is saying 13 to some power equals, again, this is about 9. So 13 to some power is about 9. This is going to have to be something, this will have to be something less than 1. Which means this is going to have to even be something smaller than 1 because we had to multiply it by 7 to get this. So again, we can say we know it's going to be less than 1 because 13 to no power greater than 1 will give me something less than 13. All right, so again, we can say it's going to be less than 1 for this and even smaller for this because we would have to divide by 7, but I just don't know that it's easy to get a really accurate estimate at that point. But we shouldn't be surprised that it's less than 1 if we ask that question first. All right, let's take a look at this one. And again, if you want, you can go ahead and plug that back in here and just check for yourself to make sure that it works. So we could do 7 times 0.1231, and we'll get 0.8617. And then we'll take 13 raised to, oh, I just lost it. Hold on, let me do it again. 7 times 0.1231, I get 0.8617, and I raise 13 to that power, so 13 caret 0.8617, and I get that, and then I multiply it by 8, and I get 72.94, which is very close to 73. So you can check it by plugging it back in and doing it just like we've checked other equations if you really are afraid that that's not accurate. All right. Okay, let's try this one. Same idea. We've got a lot going on here. We've got more in the exponent than just a single variable, and we've got a coefficient out front. So let's divide by the 9. So we're going to get 9 to the k plus 2 equals 59 over 9. Again, let's kind of estimate this. If we did 9 times 7, that would be 63, and 9 times 6 is 54. So 9 to some power is between 6 or 7. Again, this is going to have to be less than 1, which means when we subtract 2, we have to subtract 2 from something to get less than 1. So k maybe ends up somewhere around 3. We'll see. Or in the high 2s maybe. All right, so let's do it. Let's write it in logarithmic form. So we've got log base 9 of 59/9 equals k plus 2. All right, we'll do the change of base formula. I'm going to choose to do natural log this time because, again, at this point it does not matter which one we use. It will in just a second. So natural log of 59/9 over natural log of 9. Natural log of 59/9 divided by natural log of 9. And we get 0.8558. And again, this has to equal this because they were both set equal to equal expressions here. So 0.8558 equals k plus 2. Subtract 2 from both sides. Wow, I was way off there. Minus 2 equals, and I get k equals negative 1.1442. Yeah, sorry, I wasn't thinking there. I need that to be less than 1. So I need this to be a negative number right here, yeah. Okay, again, feel free to plug that back in and try it. All right, I want to look at one more like this on this side, and then we'll switch to a couple problems on the back, on the next page. So here I have just a plus 4 on this side. So this time, instead of dividing by a coefficient, I'm going to subtract that. So I get 17 to the 10 minus k equals 62. And again, if I want to make a guess, I can say 17 to what power equals 62. It's going to be somewhere between 1 and 2 and much closer to 1 than to 2. I'm going to rewrite in log form. So this is log base 17 of 62 equals k minus 10. I'm going to use the change of base formula. So this is log of 62 over log of 17. Whoops. And I get 1.4567. 4, 5, 6, yeah, okay. And that has to equal k minus 10. So I'm going to say k minus 10 equals 1.4567. Add 10 to both sides, so I get k equals 11.4567. All right. Okay, we're going to flip to the next side. Okay, on page 126, we're going to try 15 and 17 together. But you should notice something different about 15 and 17 than on all the problems on the other page. And in fact, the previous, well, these three problems here have that same property as the previous page. All their bases are whole numbers. But here the base is E, it's E. In fact, every other problem on the rest of the page, besides those three, has a base of E. So don't let that freak you out. The only thing that we're going to notice here is it's far easier when we use natural log instead of choosing log base 10 for these. So let's do what we did on the previous problem, which is we're going to get this by itself, which means we need to move the 6 over. So this becomes e to the r plus 4 equals 23. Right, again, as with all the other problems, we change this from exponential form to logarithmic form, but we're going to change this to log base e, which is the same thing as natural log. So usually when we have that e or the base written down here, we don't need to write anything. And then these two flip-flop positions right here. So this becomes natural log of 23 equals r plus 4. Again, if you really want to write it with that base there, you can. You can write it as log base e of 23 equals r plus 4, but I strongly encourage you to ditch that and just write it as natural log. Okay, so this, it's actually a lot easier when we do this, because then we can just use the calculator to find natural log of 23. So we're just going to type that in. Natural log of 23. And we get that this is 3.1355 equals r plus 4. We're going to subtract 4 from both sides. And we get r equals 0.8645 negative. All right, the problem with the e's, they're easier to solve, but the problem is I just have a hard time with intuition and these, like I did when the base was a whole number. Because if we're at this point and we're saying e to what power equals 23, I don't really know, because e is around 2.7. So I can't use like my whole number, intuition to figure it out. So maybe I would say e is about 3, so 3 to what power equals 23? So 3 to the first is 3, that's too low. 3 to the second is 9, that's too low. 3 to the third is 27, that's too high. So maybe we would say somewhere between 2 and 3, but remember, we estimated that to be a 3, which is way too high. So maybe it's actually closer to 3, or higher than 3, instead of saying between 2 and 3. All right. So in fact, we found out that it actually is a little bit higher than 3 when we did that. 3.1355. And then, but that's just this. And then we have to subtract the 4 and we end up with a negative value. All right, let's try this one. All right, so here what we're going to do is, again, we've got this that we're trying to get by itself. So we need to move this over and this. So just like we do in regular algebraic equations, if we had 5.9x plus 0.7 equals 43, we would move this first. So this is going to be 5.9 times e to the 10x minus 8 equals, and then when we do 43 minus 7, we get 42.3. Right, we're going to divide both sides by 5.9, so we get e to the 10x minus 8 equals 42.3 over 5.9. And now I'm going to change it into the natural log. All right, so I'm changing it into logarithmic form from exponential, but I'm specifically going to use log base e, which is natural log, and then these two flip-flops. So this becomes natural log of 42.3 over 5.9 equals 10x minus 8. Right, I'm going to do that in my calculator. So I get natural log of 42.3 divided by 5.9 and parentheses. Now notice it's not two separate logs like it has been before in the change of base formula. We don't need to change the base because we have a button to do this already. So both of these numbers end up in the single parentheses at one time. Right, so we end up getting, oops, that didn't type in properly. That's 5.9 end parentheses. All right, so we get 1.9698. So 1.9698 equals 10x minus 8. I'm going to add 8 to both sides. I get 9.9698 equals 10x. I'm going to divide both sides by 10. What that's going to do is move this over one place. So we've got x equals 0.99698. But again, it says round to the nearest 10,000th. So that's this place right here. So we're going to have that be x equals 0.9970. All right. Okay. How about you do number 19 on your own? All right, so pause the video and do that one on your own. Okay, here's what you should have done. So you want to subtract 2.9 from both sides. So we're going to have negative 5.3 e to the 8x plus 5 equals negative 27 minus 2.9 equals negative 29.9. Duh, I should have known that. Divide both sides by negative 5.3, so we're going to get e to the 8x plus 5 equals 5.641, I'm sorry, 6415. Yeah, 6415. All right, I have to change it into logarithmic form, so this is going to become natural log, and these two flip-flops, so this is going to be 5.6415 equals 8x plus 5. I'm going to actually find out what that is, so it's natural log of 5.6415 equals, that is 1.7301 equals 8x plus 5. I'm going to subtract that 5 over, so it's going to be 8x equals, let's see, let me subtract 5 from that, and I get negative 3.2699, and then I'm going to divide by 8, so 3.2699 divided by 8 And I get negative 0.4087 is my answer. Okay, hope you did all right.